Hi guys, Mrs. H here. Today we're going to be looking at macroevolution. So we're going to be looking at the patterns that lead to macroevolution. We're going to look at roles of extinction in evolution and differences between homologous and analogous features. So again, we have some key vocabulary to consider. So remember, macroevolution is how are we changing from one species to another. Earlier, we had looked at how do we get variations within the species. So now we're looking at how do those variations within the species, within the gene pool, lead to macroevolution. How does that lead to speciation? Now, macroevolution is irreversible, right? We can't undo that. This is large scale change. Microevolution is small scale change, so changes within the species. So how do those changes within the species lead to speciation? That's what we're going to look at. And what is speciation? That's the formation or the development of a new species. So the patterns that occur with macroevolution is we have gradualism, equilibrium, and punctuated equilibrium, extinction, divergent evolution and adaptive radiation, parallel evolution, convergent evolution, and coevolution. So those are the patterns that we're going to be looking at. So the difference between gradualism and punctuated is just as it sounds. Graduated, it's gradual, right? Punctuated as we go from one to this jump, where gradual is at this incremental constant rate, right? And so if we look at founder's effect, a founder effect species. So if we look at the two diagrams, notice the change in the beak is very gradual. There's small little incremental changes occurring to the beak in gradual speciation. And if you look at punctuated equilibrium, notice it's a big jump and a big difference in the beak changes, right? That's the difference between the two. So gradual was proposed by Darwin, and it does support the traditional, models of evolution. It does suggest that changes are gradual and slow, and that this is always happening, and that we're constantly changing. Gradualism is supported by fossil forms. Punctuated equilibrium, fossil records show that not all species have traditional fossil forms. There's gaps and there's holes. And so this suggests that the rate of evolution is not necessarily constant, that it's not a gradual slow, but that there's periods of big changes. And so over these long periods of time, we won't see any changes. We get into this like stasis or this unchanging period, and then all of a sudden there's this burst of rapid change, and there's this burst of speciations. And so that would be that punctuated equilibrium. And so if we would look at this in terms of on a graph, and we charted evolution on the Y and time on the X, this is how we would see these graphed visually. So again, examples of this would be horse evolution. So if we look at the evolution of the horse, or the middle horse, which existed about 35-ish million years ago, there was a gradually evolved into, so we see gradual changes and gradual sudden periods. But then all of a sudden there was this inactivity, and there's this burst of change, and there's a burst of activity where we see many different branches on the family tree. And so the horse, actually, we see the evolution of the horse, we actually see both this gradual and punctuated. So from 32 million years ago to 37 million years ago, we really see gradual, slow changes, and then all of the sudden, boom, we see a whole bunch of different changes in the species. So how does extinction play a role in this? So extinction is part of our of life cycle. So it does occur. Um, However, the rate at which it happens, at the rate at which it occurs, is very different what we're seeing now than what we've seen in the past. So, this life cycle of these species plays a role in evolution. So, once this life cycle of evolution occurs, it's permanent. So, once we evolve into a new species, you can't go back. You can't be like, oh no, I want to be that. You don't go backwards. So, once that change has occurred, and a species has evolved into a new organism, that if that new species has eliminated or permanently removed the other species from Earth, that would be extinction. So under normal circumstances, it takes a long period of time to be extinct. We are accelerating this rate. Humans are causing a huge acceleration currently in extinction. This is not normal extinction. Um, this is a sudden, rapid event. When species become extinct, its niche, remember that's its role, then becomes available. So there's this empty space. And so that empty space will allow for new species to fill in that empty gap and that empty hole. Well, right now we have way too many holes and way too many gaps caused by human activity. So how are we doing this? Well, habitat destruction. So we're destroying their habitats. We're disrupting their habitats. So they have no place to live, and so they go extinct. An example of this is the rainforest. So we've eliminated these habitats of these birds and there's these animals that they don't have shelter, they don't have food, and so they die. Climate change. Climate change, yes, we are seeing an increase in the average global temperature. And as a result of that increase in average global temperature, we're seeing disruptions in our weather patterns. That's why we see Texas in a deep freeze right now. They had a swing in a 24-hour period of, so what was it, like 80 degrees. Their infrastructure couldn't handle the snow because they don't have snow in Texas. It's just unheard of. And so they had this huge devastating impact. So we're seeing that in humans, where we have more resources to be able to survive. Imagine the organisms and the animals living in that area that can't go call their friend and say, hey, I need help, right? And that's, imagine that you have to just stay where you're at. You have this, you're living in Texas, you're used to the 70-degree weather. It comes into to 30 degrees and you can't go buy new clothes. You have nowhere to go to shelter and to protect yourself. That's what these organisms are experiencing. And on the flip side of it, we're seeing cold areas getting really hot. And so here you have an organism that is used to the really, really cold and now is experiencing extreme warm weather. And so these organisms can't withstand those extreme temperatures. And so they're dying. So another pattern of coevolution is coexistence. And so when one species becomes extinct due to an extinction of another. So an example of this is the passenger pigeon. So imagine you are relying on an organism for your food, and that food source is now eliminated. Excuse me. So the food source is now eliminated, so you're now going to starve to death. So this is coexistence, and so as a result of one species becoming extinct, it causes another species to become extinct. This is especially a problem when we have keystone species, which many organisms rely on the keystone species. So background extinction. So background extinction happens continuously, and it's always happening. So this continuing extinction of species is called background extinction. So all species on Earth throughout time, it's thought that 99% of them have already gone extinct. And so we're always changing. The organisms on the planet are always evolving, and that's okay. However, humans again are doing this at a very too big of a rate, because other species aren't able to fill in the holes and fill in the niches. There's no standard for this. There's no standard like, oh, this is how long a species is going to survive on Earth. Some survive for a really long time, like millions of years, and some only survive for hundreds of thousands of years. But we do know that this is always happening extinction is a normal process of evolution. Okay, so mass extinction is when at least 10 there has been at least 10 extinction events in the history of Earth. This is when large numbers of species and the major like keystone organisms disappear over a very short period of time. It's usually caused by a dramatic change and a shift in the environment and in the ecosystem. That's what climate change is doing right now. It's causing a major shift caused by humans. Ice ages are an example of this. So some examples are, the dinosaurs. This is one of the ones we're all familiar with. Is the extinction. The extinction of the dinosaurs, approximately 65 million years ago. This was, again, in a short span of time, we lost many, many different species of dinosaurs. It was probably, again, triggered by a change in climate or a change in the ecosystem. They think it was a meteorite. Do we know for sure? No, we don't. But there is strong suggestion that meteorite brought on an extreme climate change. And so their environment changed, and so they can no longer adapt and survive. So they became extinct. So let's look at some other patterns of microevolution. There's divergent evolution and adaptive radiation. So most evolutionary changes appear to be divergent. So what happens in divergent? So ancestral species evolve into, there's a split. They branch off from each other. And they're becoming more specialized and occupying two different roles or two different spaces in the ecosystem. And so because they were the change in the ecosystem, there's an available niche. And so one organism has a slight adaptation or a slight advantageous characteristic, so it can fill that role. And so then those two species will then have two separate niches. So when a species diverges into a large number of species, it's referred to as an adaptive radiation. This is a rapid process, and it usually is because of a founder effect. So again, They're filling this new space. They're filling this new niche. Darwin's finches are a classic example of this. So again, this is a adaptive radiation. So again, there's slight or changes in variation in the beak, and so those beak changes allow them to feed off of different seeds or different insects. And so they're able to fill a different role or a different niche because they're having a different food source. So another pattern of macroevolution is homologous structures. Remember, homologous means same. So there is a large evidence to support divergent evolution and adaptive radiation. And then homologous features are part of the evidence to help support that. So remember the features of a homologous structure. They have similar structure but different functions. So you're going to use the same bones but in a different way. You're going to use the same structures but in a different way because you can fill a new role, right? A new niche. And so homologous structures really support this idea of divergent evolution. And we see this in, humans and all the way to the wing of a bat, right? We have the same bone structures. But the bat wing is used for flight. Human arm limb is used for lifting. And then even in the paw of a cat, it's used for walking and supporting weight. But if you look again at the structures are similar. So again, this is what I was talking about. We have discussed this in previous lectures, but again, this idea supports the function of macroevolution and divergent evolution. So we're going to use the same structures, but in a different way for a different purpose. And so as a result of that different purpose and different use, we diverge from one another. And so again, looking at the humerus, the radius and ulnar, the capillaries and the metacarpals and phalanges, all of those are present within the cat, the whale, and the bat. But again, they're used for different purposes. And so therefore they have evolved and changed over time. So parallel evolution. So this is when similar features evolve related to the species who have common ancestors, but they didn't have these features. So this can occur through selective pressures. This is debate whether or not this is actually an evolutionary pattern exists, or if it's actually more of a convergent evolution. And so parallel would be these two species are side by side as opposed to convergent. And it's not extremely debatable, but there is some controversy here. Convergent evolution, these are species which have similar ways of life. So, they're live in similar habitats. They have similar niches. And as a result of the similar niches, they're going to have an analogous structure. So an analogous structure, the structure is not the same, but its function is the same. So think of a wing of an insect and a wing of a bat. Those structures are made much differently. Their structures look completely different. However, they have the same function. So this would be an example of convergent evolution with analogous structures. So again, here are some of those examples. So swimming, we've got it on the flipper, the wing, and the fin on the shark, the penguin, and the mammal. So these would be examples of your analogous structure due to convergent evolution. So again, this is showing how we can have changes within a species or within an environment that would cause speciation. This will cause a change within an organism so that it would become independent of the rest of the species in the community and become its own species in its own right. Coevolution occurs with unrelated species, but they evolve together. And so this occurs again when there's a strong relationship, maybe between predator and prey, or plants and their pollinators, or herbivores and their food sources. So you have a situation where one organism is relying on another or has a relationship with another. So if one changes, the other one has to change as well. And this is again a selection pressure that brings a change. So we're seeing a change in one species going to result in a change in another species. So example of this is, so if the flower um, it changes, then the hummingbird has to adapt to that change, and so it will evolve as well. Same thing with insects, flower, right? So their food source changes, so they have to change along with it, or they will become extinct. The organism previous will probably become extinct. So this would be a situation where you could have coevolution with extinction. So the new changed organism becomes independent of the other, causing a new species. The other one hasn't adapted, hasn't changed it, doesn't now have a food source, so it's going to die out. So let's do a comprehension check, answer a few questions, and see how you do. So how'd you do? So again, on this unit, we were looking at how these changes in gene pool will then result in a change in the macroevolution. So I know some of this was a review from last week, but now we were kind of tying all these things together. So if you have any questions, make sure you're reaching out to me. Bye, guys.